Hi, welcome back to my channel. Well, in this video we'll be doing an analysis regarding a very important design which is known for its flexibility, that is known as completely randomized design, and sometimes it is usually known as zero-way elimination of heterogeneity designs because of the fact it is usually used under the conditions which are homogeneous in nature, or we can say where the experimental material is homogeneous. For example, we are conducting the experiments in labs, we are conducting the experiments in nurseries, especially in greenhouses or mist chambers. So that is why it is known as zero-way elimination of heterogeneity. And why this is known as a most flexible design, because in this design we can use equal number of replicates or unequal number of replicates across the treatment. So we have a liberty to use equal or unequal number of replicates because the experimental material is homogeneous, which is not quite possible in case of other design, especially to the randomized complete block design. So in order to proceed, we have 4 treatments and every treatment is replicated 5 times. The first important step is to get the sum of all treatments across the replicates. We'll use the sum function, then we will simply drag all these, then we'll get the average. So this is a preliminary requirement because averages are very important or required to get the comparisons, because all the comparisons across these 4 treatments will be done based on these averages. Then we'll highlight. Now the next step is to get the grand total, which is nothing, it's the sum of all these observations, or we can say the sum of all these totals. Then a very important step in order to get this ANOVA table is to get the correction factor, which is nothing, it's the square of this grand total divided by the total number of observations. And here we have 20 observations because we have 4 treatments and 5 replicates. So 4 multiplied by 5 is 20. So simply we'll click on this, or we can put this, good thing is to put this cell in brackets, then raised to the power 2 in order to get the square of this value, which is a grand total, divided by 20. So we have the value of correction factor, then the total sum of square. That means we have to square each and every individual observation at the same time and add them. For that we'll be using a function, inbuilt function, that is sum of squares. Okay, we will highlight all these values. Then what we have to do, simply we have to deduct this whole value with the correction factor. So we have total sum of square, then treatment sum of square. We need to get the square of totals of each treatment. For that we have this 45 square plus 50 square plus 60 and 65. For that we'll be simply using this sum. Then we'll highlight all these. Okay, then we have to divide all this value with the number of replication, that is 5 in this case. But the next important thing is that this whole value is to be deducted with the correction factor. So we have treatment sum of squares. Now the error sum of square is very simple to get. Simply total sum of square minus treatment sum of square. So we have to do it like this. This is total sum of square minus this treatment sum of square. So we have to put these values. So we have got the value for total sum of square, treatment sum of square and error sum of square, and we have to put all these values within this ANOVA table. Now the important thing here is we have only 2 sources of variations in this case, in this design. One is because due to treatments and another one is due to error. While in case of RCBD, you'll find one more source of variation, that is due to the introduction of a very important principle that is known as local control. You'll find a column or a row of replications or blocks. Actually these are blocks, because in case of RCBD you have equal number of the replications are equal to the number of blocks. So in this case we have only 2, one is due to treatment and one is due to error. And to get the treatments, degrees of freedom for treatment, simply since we have 4 treatments, that's 4 minus 1 is 3 here, and error, the degrees of freedom due to error is total number of observations. Then we have to subtract the total number of treatments. The total number of observations is 20 and 20 minus 4 is 16. Since the total number of observations are 20, 20 minus 1 is 19, or you can simply add both because this is additive in nature. Simply we'll put the first treatment sum of square. We have this value, we'll put it here like this, but we have to use this spatial option here. Then error sum of square. Okay, then copy, we'll place it here. Again the same spatial option. Then we have to get, since these are the variations, and these, when we divide these variations or these sum of squares with their respective degrees of freedom, then it becomes variance. In order to get the mean square due to treatment, we will simply use divide this sum of square with its respective degrees of freedom. Then we'll press on this enter. So we have mean sum of squares or mean square due to treatment. Then we will drag it. That means this divided by this, we will get the mean square due to error. Since we need to get a variance ratio test which will authenticate whether all these four treatments are significantly different from each other, for that we will simply use the ratio of two things: mean square due to treatments upon mean square due to error. So we have this f calculated. Now we need to get the f tabulated value because we have to compare this with, because we don't have an option of p value here. So we'll simply use that basic thumb rule. If the calculated value will be greater than tabulated value, then we will reject the null hypothesis that all these four treatments are significantly different from each other, or vice versa. Simply we'll use this function finv. Then the probability level, we will choose the default one, 0.05, because then after that the degrees of freedom due to the treatment, then the degrees of freedom in the denominator, that is due to error. Then simply we'll press on the enter. So we have tabulated value here. We can conclude at the first instant that since the calculated value is greater than tabulated value, since the calculated value is less than the tabulated value, so we can conclude all these four treatments are not significantly different. So we don't have any evidence to reject a hypothesis which is saying yes, all these four treatments are equal. So from F we can decide whether the treatments are significantly different or not, whether we can reject a hypothesis or not. But for the sake of calculation, we'll calculate the standard error of difference of mean, which is under root of twice mean square error upon the total number of replicates. We'll simply use this SQRT option here, then 2 star the value of mean square error. Then we will put a bracket here also, whole divided by, we have 5 replications, and we'll click on this enter. So we have this standard error of difference of mean. In order to get the CD is nothing, this is the multiple of standard error of difference of mean with the value of t at a respective degrees of freedom with a chosen level of significance, 5% in this case. For that I will be using this tinv function, which I have already mentioned in my previous video on RCBD. Then the appropriate degrees of freedom, which are in context to error degrees of freedom, that is 60. Then multiply by, we'll put the star sign with this SEDM, then enter. So we have CD values. Now we want to put a significant sign before this. Since already it is non-significant, then how to put it? We will use this if function. If the calculated value is greater than this tabulated value, then we will use this S symbol, which is significant. Then if again this calculated value is less than this tabulated value, then we will use NS, and automatically this NS sign will be popped up here. So you can see, although it was here it was concluded that they are not significantly different, they are same, and we don't have any evidence to reject this hypothesis. But if had this calculated value would have been greater than tabulated value, then the calculation of critical difference would have been worth. But for the sake of just calculation and to show you how to calculate the critical difference and put the signs before this, that's why I have shown this formula here, if formula. So this design is usually used whenever we are doing the experimentations or experiments in labs, where we can control or maintain each and everything. We can control temperature, we can maintain the humidity, each and everything. And this design, we don't need to worry about the number of replicates, how many replicates for a particular treatments we can use. We can use equal or unequal also. Since this video was based on equal number of replicates only, in the next video I'll be doing the same step-by-step analysis in case of CRD, but with unequal number of replication, how to do it. Here again I will make an announcement here that which I have already made in my previous video, that why we used to do or perform this kind of analysis or the basic experimental designs in spreadsheet of Excel. Because here we can put simply the values of other variables here and we will get done, because we have a liberty here to do a certain kind of adjustments with our data if the things are not in accordance to what we have expected from a particular variable or the particular experimentation. So the adjustments or a certain kind of manipulations can be done by means of this spreadsheet. Hope this video will do a bit justice with the requirement which I have already announced in my previous video. In next video I'll be doing the analysis regarding the same experimental design, but that will be based on unequal replicates. If you have any suggestions or comments, please text them or post them on the comment section below. Thank you very much.